Okay, we're going to talk about permutations and some word problems. You should have already watched the difference between linear and circular permutations, and also the counting principle. And basically, the thing you need to know about permutations is these two words, arrangement and order. If you see those two words, you know it's a permutation. The formula is giving like this. Your TI 83 or 84 has this this formula on it that you can use, or you can just use n factorial over n minus r factorial, which means n objects taken r at a time. Okay, if you watch the counting principle video, it's basically the same thing we did there. So let's look at some word problems. I think I have 7. So we have a word problem that says, how many ways can 8 members of a family be seated side by side in a movie theater if the father sits on the aisle? So basically, the way I do it is I just draw 8. 1, 2, 3, 4, 5, 6, 7, 8. There's only one way to seat the father. Then the arrangement's important. The order's important. So we have 7 members left. So this would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So basically it's 7 factorial if you want to do it that way, which is 5,040. All right? And if you use the formula, it would be just n objects taken r at a time. So that's how you would set it up. But we just use the counting principle here. Now, in this case, we have number 2, the bride and groom and 8 members, so that's total 10, are seated around a round table. So it seems like it'd be circular. However, the bride and groom has specific seats. Since there's a fixed point, this means it's linear. Alright? And so if I were to do my little 10 slots here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, my bride and groom has specific seats. I don't know what they are, but I'll just put bride and groom here. So that's just 1 times 1. And we have 8 members left. And so from there, it's just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So basically it's just 8 factorial. And we're just using the counting principles before, and that would be 40,320. Now, in this case, this is our books, 3 books chosen from a selection of n objects of 7. So basically this would be P in R, which equals P 7, 3, which is 7 factorial over n minus r factorial, so 7 minus 3 factorial, which is 7 factorial, I should have saved more room for this, over 4 factorial. And basically, man, I should have saved more room, so I'm going to erase some of this. You have that down, hopefully. So it's basically 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. So basically you get 7 times 6 times 5, which equals 210. Now, if you wanted to, you wouldn't have to use the formula. You could have just said, well, I have 7 books, and it does use the word selection. I prefer the word arrangement. You're arranging 7 different books. And you could say, well, there's 7 ways to choose the first book, 6 ways for the second, and 5 for the third. And you get the same thing. All right. The next problem we have is, How many ways can 8 campers be seated around a campfire? Now, this is a circular permutation, and so this is based on the other video I did. We're just going to do 8 minus 1 factorial, which is 7 factorial, which equals 5,040 ways. Okay? Now, this one, a photographer is taking a picture of a bride and groom with 6 attendants. How many different ways can he arrange the people in a line if the bride and groom stand in the middle? Now, this one is a tricky one. So we have 8 slots here. 1, 2, 3, 4, 5, 6, 7, 8. Now we have the bride and groom. And so we have 6 people left. They're in the middle. So we have 6 times 5 times 4 times 3 times 2 times 1. And if you were going to stop there, you would be wrong. So this would be total 6 factorial. However, you could have also done it this way. 1, 2, 3, 4, 5, 6, 7, 8. And you could have done 6 times 5 times 4. But the groom stands here and the bride stands here. Notice how this one's different than the previous problem we did. And that would be 6 factorial. So we have 2 times 6 factorial. Or you could have just said there's 2 ways to do the middle. So there's 2 ways for the middle part. Then we have 6, or we could have, 1, 2, 3, 4, 5, 6, and done it this way. So basically you'd have got the same answer. Because there's 2 ways to do the middle. And the total would be 1440. So that's 1440 ways. How many ways can Laura and her 6 friends be seated around a table? Flora sits at the head. So it's around a table, but Laura has to be here. And so there's 6 ways. So this ends up not being a circular permutation because we have a fixed, Laura has to sit, we have a fixed point. So we have 6 other ways to go. It's treated as a linear permutation, which would be 720. If you want it, you could do, since Laura counts 7, you could have done 7 minus 1. That still gives you 6 factorial. So either way you look at it, it's 720 ways. And I have, how many ways can 5 men and 5 women be seated alternately around a table? So basically, we have a table here. All right. And men and women. So I can put man here. It's 5, right? Let's see if I can do this. Man here, man here, man here, man here. Then woman, 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 woman. Now where I started is with the man here. It doesn't matter what man. So in that case, I have 5. For the men, it's 5 minus 1 factorial. And for the women, it's 5 minus 1 factorial. Okay? But the problem is we could have seated the woman here. So there's another possibility. So I could have put the woman at this spot and went around 5 times. And then put the men in the different seats. Remember, there's 10 seats here. Men, 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 and men. And in that case, it would be 5 minus 1 factorial. this would be men times women. This would be women times men. All right. So in this case, it's 2. We have 2 different ways. Here's the first way. Here's the second. So that's 2 times 4 factorial times 4 factorial. And the answer would be 1,152 ways. You need to think about this one. Okay, the next video I'm going to talk about shortly is mirror type permutations or ring permutations. Thank you and have a nice day.